All right, we are doing ECGR 4161, lecture number 8. And we just had a quiz, just thought I would go over the solution to the quiz. It's really not as hard as you think it is. How many of you think you got it? All right, 2. Not good. All right, so let's take a quick look. Here's the problem. Given the following information, 12-bit ADC plus reference of 5 volts minus reference of 0 volts. And oh, by the way, the digital representation is. So the first thing to say is, what is the step size? Well, as we said, you go from your lowest number over here, 0, 0, 0, 0, 0, 0, 0. How many zeros am I up to now? Oh, we've got a total of 12, right? 0, 0, 0, 0. And it's going to go all the way up to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And this is going to go from 0 volts to 5 volts. All right? So obviously somewhere between here and here, you go up by individual steps. So the question is, how much is each one of those step sizes? Each one of those step sizes is going to be 1 over 2 to the 12th. Right? Multiply that by 5 volts. And your number is, what's 2 to the 12th off the top of your head? That's
4,096.
4,096 divided by 5. And if you didn't have a calculator, I would accept that. And the answer is
0.000122.
Do you know that for sure?
819.2.
What is it?
Oh, never mind. 0.001222.
1.22 millivolts per step.
1.22 millivolts.
You got that one?
All right?
I think which one was digital.
So, now you have the value, which is 1000, 0011, 0010, and whatever that is converted to base 10. Then you take that and you multiply that by 1.22 millivolts, and that's going to be equal to, and that's your answer.
2.5, 6.
Oh.
That's it?
That's it.
Wait.
Wait.
I didn't
Rewind.
That.
You didn't catch that last one.
I at least got that part.
Well, I'm going to get there. So my 1000, 0011,
You're done on decimal.
0010.
You're done on decimal.
What? Ah, crud. Sorry. Ooh, wow, that's pretty amazing. 1000, 0011, 0010. Convert that into decimal. That's 2098.
That's all right.
That ain't good. Got 50 at least.
Pardon me? Times 0.00122 turns out to be 2.56 volts, which seems about right because this number is about half of what the entire range is. 2.56 is a little bit more than half of what it is. I provided this down to you just to remember what the concept is. Here, I'll do that again. I provided this at the bottom just so you can remember what the concept was. If you wanted to, you could have even, for the first problem in here, said 1 is equal to V in, which is what you don't know yet, times 2 to the n minus 1, V ref, which is 5, plus 1/2. Take the integer of that. So for all intents and purposes, I'm close. 4095 is what the formula would have come out with. but I would accept both because they're just about the same. What is this? This is the same as Vn is equal to 5 over 2 to the n minus 1.
Minus.
This
Minus
dropped out.
0.5.
Yeah.
Really?
And what do you know? That's what I said up here, right? 5 volts to the 12th. Was that easy?
Yeah. It is now.
It is now, yeah. So, provided you got your name correct, you will get at least some points. Woo! Glad you're all excited about that. As you should rightly so be. Oh, Mr. Morgan. Morgan.
Yeah. Freeman.
You didn't pick
You
this
got
up
A1?
last time.
You got A1? You get A1?
Huh?
You get A1?
I got part of it. Right.
All right.
I got part of it.
So let's do another little recap. Or do I need to do another recap of A to D?
Oh, why not?
After this one? Well, let's look at an application to see why you would need that. And so if you remember at the end of last class, I was talking about an infrared detector, right? So here's one that you're going to see very soon. It is the Sharp Infrared Rangers, not to be confused with the Texas Ranger, but it is a device. Let's see if we have a picture in here. And we see what it looks like from the side. You have this device here, that it has a V out, a ground, and a VCC. So introduction, infrared, sophisticated. They're talking about the interfacing, the connector that you need, stuff like that. For those of you who are mechanically impaired, they even tell you how to connect it. All right? Yeah, way. So, here's I tell you what it works. Infrared detector will take continuous readings every 32 milliseconds. So notice that. So that means that this is limited to a frequency of what?
One with that.
Which is?
One over.
Which is? So our
500 something megahertz, something like that.
Sharp IR Ranger GP2D
32 milliseconds.
120,
seconds?
It's a minute.
32 milliseconds,
31.25.
Hertz?
period.
That's it?
Yeah.
Frequency is equal to 1 over 0.032 seconds, which is equal to, oops,
31.25.
31.25.
31?
20.25 hertz.
31.25 you said,
Yeah.
okay? Oops. It is seconds at the bottom. And that is the definition of hertz. So you can only measure it every 31.25 hertz. You can actually read the value more frequently than that, but it won't change. So if you read it once every 100, or if you read it once every millisecond, you'll get the same measurement for 32 times. If you read it once every 10 milliseconds, you'll get 3 of them that will be the same. Sometimes 4, right? Why would it be 4?
Round it up.
What time is that?
Well, if your measurement is like this, and then it changes for, let's see, that's 0, 10, 20, 30, 40, and then 2 milliseconds later it goes up. Well, it just so happens if you read it at this point in time, 2, 3, 4, it'll be 4 in a row. That'll be the same value.
You're saying if we read at a frequency higher than that, right?
So if you read it now, as opposed to what I described earlier about aliasing, you know, how will it differ? Again, this is not necessarily a periodic signal. It's very, not random, but it's very slowly changing. Unless you have a vehicle that moves extremely fast, all right? Well, I guess another thing to take a look at is what is the range, and you've seen a picture like this before. What do they say? They say that the analog output is connected to an A to D converter and can be used in a circuit. Shows a typical response curve. Notice the distance down here, centimeters. It looks like it works pretty good up to 75 or so, and this one says 10. But actually they'll discuss later about variations. In fact, let's take a look at this. The specific part is the GP2D120, and when you're running it at 25C with VCC of 5 volts, you can expect the range is going to be from 4 to 30 centimeters. 4 centimeters is how much? About 1.5 inches, right?
Yeah.
30 centimeters is about what? 1 foot. So obviously, if you're going to use it, it has to be more than an inch off the ground to be worthwhile. And that's better than some of these other ones. If you look at this one right here, this one says its minimum is 10 centimeters. So using it as something to reflect off the ground, it might be a little bit better. Oh, excuse me. Oh. So what they're saying is at 30 centimeters, you can typically see your voltage is going to be anywhere from 0.25 volts to 0.55 volts. And the expectation is that when it's at 4 centimeters, you're going to see it, they say a delta V is going to be 2.25 volts to 1.85 volts, which means what is the voltage? What is going to be the typical voltage at 4 centimeters that you'll measure?
2, 4,
2.
2.
1.95.
Says 2.
I like this. Well, if the difference between these two right here is going to be typically 2, yet at 30 centimeters it's 0.4, you would expect that the curve would say at, let's see what our curve was right here. At 4 centimeters, it would have a difference, and this is at 30 centimeters. It said at 30 centimeters, your typical voltage is going to be 0.4, and then the difference up here is going to be 2, so that means this will be 2.4 at 4 centimeters. Which means that this curve is somewhat representative if this number were 4 and that number were 30.
We're not able to see the bottom.
Oh yeah, there we go. If this number were 4 and that number were 30, that would be the typical curve. So here's a good question for you. So we're going to see, and it is not a direct line, it is going to be a curve. Now usually what they include in a book like this is an indication of what the typical formula is for that curve. And unfortunately, I cannot find one in this book. So typically what you have to do is you have to go online and look for the data pages. So let's look it up.
You getting our test back today?
Say it again?
You getting our test back today?
No. I have to do something this week called, or I had to do something this last week called helping people get ready for moving. So I'm only halfway through the tests. They don't look good, by the way, so,
Really?
no.
Score.
I should say, for some people, they don't look good. Oh, for heaven's sakes,
Hope I'm not
open.
met some people.
Pardon me?
Said I hope I'm not met some people. Fingers crossed.
All right, so here's the data sheet for this from Sharp themselves. This book that I had shown you is from somebody who sells it. So this from Sharp shows you some of this typical information as well. Oh, in this case, they say it's 2.25 instead of 2. So that's even a little bit more different. We have, I'm looking for the formula of the curve.
Analog voltage. Distance reflected.
This is a nicer curve. So you notice here it says 2.8 volts. And down here, which is where they're recommending the distances at 30 centimeters, it's down to 0.4. And they even have a different value for white and gray when it gets towards the end. Where's my formula? Where's my formula?
No formula.
No formula. Well, one would have to create their own if they wanted it to be fairly precise, and it all depends on how it's manufactured. So let's think about this. If you were an engineer and you wanted to characterize about what this curve would be, do you think it would be safe just to say, ah, good enough, let's just do this?
No.
Or how would you go about determining what that curve is?
Break it up into intervals.
Say that again?
Break it up into intervals, like measure at each.
All right.
point.
Maybe measure at a couple of distances. So perhaps you can write a small little LabVIEW program to say, all right, I'm going to hold something 4 centimeters away, now measure it. Now I'm going to hold something 10 centimeters away, now measure it. Now I'm going to hold something 20 centimeters away, now measure it. And now I'm going to hold something 30 centimeters away, now measure it. Even if you're close, for example, you notice here is going to be your biggest slope. Even that's a better approximation than this entire slope right here, from one point to the other. You can even go halfway in the middle and you get something a lot better than just a single straight line. Now, let's say you were writing a software program to say, how far am I? What do you think you would be doing in software to measure? So what I would like you to do is break up between you and one other person sitting next to you and write your choice. Write a C set of C code, do an algorithm, just give me steps of what you would do in English, and just let me know what do you think you would have to do to be able to identify where that is. Keeping in mind that, hey, remember what this is.
I mean, we use it this
Here, I'll just show this.
Let's see. You can use this.
Did you get pause? All right, we are back, and the common response to me was, "Holy cow! I don't know what to do." So let me tell you, or let me give you one idea of what I would do.
Multiply.
Number one, it comes in 2 steps.
8.
First, I would sample measure actually there's a couple things you can do. I'll give you one idea. I would sample measure several points and then I would do a curve fit equation. And I believe Microsoft Excel will do that for you, right?
Linear.
It will give you an equation that you can use. So the aspect of this will be to create a couple of points, and then you can feed those points into Excel and get out your formula. Since this is a second order, right? So it's going to be ax squared plus bx plus c, right? Something of that order. Then the second step is to program the following algorithm.
We assume that this is done.
Measure A to D value. Use formula to determine distance. That's it. And if you are doing this,
That's
you
what we
do
said,
something
bro.
like print.
Exactly what we see.
Use
Nothing idea.
distance.
One deal by deal.
Yeah.
Counts.
Exactly what we wrote.
Oh, wow.
Conrad.
Is it exactly what you wrote?
Pretty much.
All right, there you go.
We didn't think of that either.
Wasn't that hard, was it? Well, you guys try to make things way too hard, don't you?
When you do the curve fit after that,
When you say,
how do you
find
get
the distance?
how do you get the distance? You know your voltage value, but you don't necessarily know what distance that corresponds to.
Well, that's what you
Isn't that
have to
the
use
equation
this
for?
best fit to determine. Because each one of these points, you're supplying the x, right, and you're trying to find the y.
Got it.
We assumed that the sensor had a database. Wire.
I was in that car. too.
All right, there is another one. Option 2. One.
Yeah, can you do the second part of that by just assuming that you already know the distance equation? The voltage to distance?
Yeah, you can do, if you already know the distance equation, build a database of voltage versus distance. And what we know what the voltage is? Well, let's say we have an A to D converter, which is going to be 8 bits. So you can have a table. When the voltage that you're measuring is 0, 0, 0, 0, 0, 0, 0, 0, then your distance is going to be, let's see what we're saying here.
4 seconds.
Or we can actually ignore a lot of the stuff. Let's see, we said the maximum was going to be 2.5, or the minimum was going to be 0.4, so whatever you figure it out, somewhere along here you're going to say something like 0, 0, 0, 1, 0, 0, 0, 0, 0, and you expect the distance of this is going to be 30. Actually, we'll say 300. All right? That's 300
Well,
Meters?
millimeters. And then maybe 0011, 0001 is going to be 302 millimeters. And you'll keep on going somewhere, and when you get closer to what, a little bit over 2.5, maybe 1001000 is going to be close to, oops, I went the wrong way. Would be 298 millimeters. And then this is going to be close to 42 millimeters, and then 10010001 could be 40 millimeters. And that's a table or an array that you'll set up beforehand. You'll actually embed that in your software, just by creating an array and entering all these values. Everybody know how you would do that? How would you create the array?
Yeah.
no.
Do I need to put that out there?
Good.
Sure.
All right, so you would say something like this array.
Can you move it?
If we have 800, or I'm sorry, if we have 2 to the 8th, that's how many different values? 2 to the 8th is what? 256?
6.
55.
Equal to, in fact, here,
Curly bird.
if I'm going to do C, I'm going to say, I'm going to even make this int. Dist array 0, 0, 0. Am I doing this right? Or do I have to say how big it is first? I forget. I think I do have to say 256.
Then you get equal in curly braces, like you enter anything you want in
There
there.
we go. 0, 0, 0, 0, 0. Because all the first values are worthless, right? Because the first values are worthless because if we look at this, the value could never be, that's not possible. Or it's not worth it. And then eventually you'll get into the value 300, 298, 296, it'll keep on going. And then you'll reach 42, 40, 40, and then you'll probably go back to 0, 0, 0, 0, until you get to a total of 256 of these values. And then when you actually use it somewhere, again using C, you'll say something like what did I say in this? Measure A is equal to ADC port 0, for example, if we hooked it up to the port 0 of the ADC converter. And then you would say distance is equal to dist array measure A. Look easy enough? So again, that was option 1 and option 2. And I think I've kind of beat this to death, so let me go on. Any questions before we go on? Anybody scared?
Yep.
Yeah?
Yeah.
I'll tell you what, let's take a break. All right, we are now done with A to D, and I want to move off into another area that's more digitally based, and that is range finding using something like ultrasonic. So, let's think of nature. And let's say we have Batman or just plain old bat. Let's see if we can get this right. Does that look pretty good?
That is a nice looking bat.
Isn't it though?
That's
Yeah.
All right. You're familiar with what a bat does to collect its food, insects, stuff like that.
Yes.
It flies around in a wicked pattern, and it actually sends out
sounds.
an ultrasonic sound. And if there is a insect out there,
You will bounce.
you are a tough crowd. All right. I do have to admit, no, I have never been an artist, and I've never played one on TV.
Don't dolphins do the same thing?
Say it again.
Don't dolphins do the
Yeah.
have no
Yeah, they
idea.
do.
Yeah, they do.
All right.
Long in water.
But I don't mess with dolphins, so I don't mess with bats either.
Whales also.
The same concept. Well, if you think about dolphins, the medium is water, and in fact, water is a very good conductor of sound waves, an extremely good conductor of sound waves, a lot faster than air.
35 times faster. Learned that in scuba diving class.
35 times faster than air. But I believe that sound will dissipate faster in water than air, correct? So your range is a lot better in air than it is water.
Yeah, I think you might be right.
Because basically a sound wave is moving energy that is compressed. So obviously if you're compressing a lot of water, a lot of density, it's anyhow going on. So imagine this. What is the speed of sound?
70 something, yeah.
And I
Changes
change
with altitude, right?
Yeah, it changes with temperature, altitude, all sorts of things. Hey, let's say a nice rough estimate is 330 meters per second. Because that's about the ranges that we're going to be working with. I think if you go online, you can actually poke it into some sort of calculator, and at sea level, it's 336 meters per second, and stuff like that. So if a bat sends out a chirp, and 1 second later, it gets a response back from that chirp, how far away is that insect?
330 meters.
That's half.
330 meters.
All right.
160.
What?
So 1 second
Half it, yeah.
will travel a total of 330 meters per second, keeping in mind that it has to go there and back, so that means it will be 165 meters away. Correct? So, if we have a wheeled vehicle, and we have a ultrasonic sensor on this, and you have a wall, and it is sending its chirp to you, or to it, and then it's getting a response back. If it takes 0.1 seconds from the chirp to get the response, how far away is it?
Depends on how fast it's moving.
All right? It is 16.5 meters away. Right?
That's sitting still, right?
That is if it's sitting still.
What's that?
So you never know if a quiz question may show up that asks you if the vehicle is traveling at a certain speed, what will be, and when it sends its chirp. Well, in fact, here. Let's see if you guys can figure this out. Yeah, we got plenty of time. Problem. If a vehicle with ultrasound sends a chirp, ping, whatever you want to call it. Let's call it a ping. That's nice in our world.
We can see what you write.
Oh, that would be nice. Ping. Is moving at 1 meter a second, and a stationary object is 30 meters away, how long will it take for the chirp to be reflected back?
Is it 30 meters when it sends it or when it gets it back?
30 meters when it sends it. So,
It's actually only 29 meters.
say that again? So it is 30 meters away when it sends the ping. How long will it take until it gets the chirp back? So what I would like you to do is, since you are wonderful seniors and graduate students, this is another example of problem solving. Tell me how you'd solve the problem and tell me what the answer is. We'll take a break and let you figure that out. All right, this is now a continuation of the lecture where we were looking at this following problem. If a vehicle using ultrasound sends a chirp, is moving, stationary object 30 meters away, how long will it take for the chirp to be reflected back? So what this is a simple physics problem, constant velocity, so we don't have to worry about any derivatives. So let's take a look and let's set up the problem. We know for a fact that if this vehicle is here, there's my ultrasound, and it is 30 meters away, we are pretty sure we'll know how long it will take for that to be transmitted, correct? And that will be what?
Need speed of light.
30 meters.
Speed of sound.
And we divide that by 333 meters per second. And that's the time in one direction. And so the answer is going to be 0.09090909. I think that's enough significant digits. Seconds. Now, I guess one question could be, how far did it travel? Did the vehicle travel in that time? And so that's a fairly easy assumption to make, because at the one point where the wave hits this point, we know that it took 0.09090909 seconds, and we know our velocity is going to be, of this vehicle, is 1 meter per second. So our total time is going to be, our distance, I should say, is going to be 0.09090909 meters. Now we need to look at the next part of the problem, where we have the wave, the sound wave, and it is going to be reflected back. And at the same time, the vehicle is traveling. Ooh, it's traveling so fast it's above ground. And I guess one thing I made it a little bit too complicated is, what sort of problem is this like?
Two trains?
Two trains, exactly. Train A travels in one direction, train B travels in another direction. How long does it take? So to digress a little bit, let's think about that. So if train A travels in this direction at a speed of 50 kilometers per hour, and train B
Can't see.
travels in this direction at 50 kilometers per hour, and the whole idea is that you have train A going this way, train B going this way, and the distance is 100 meters, kilometers. Just by investigation, you can easily see that how long will it take for one train to get from this point to this point? 2 hours. So our formula here is going to be the velocity of A times t plus the velocity of B times t is going to be equal to our distance. In this case, velocity is going to be 50 kilometers per hour times t hours plus our velocity of B, again 50 kilometers per hour, our time t hours, which is going to be obviously 100 t this is 100 kilometers times t, or t is equal to oops, no, that's time t.
Yeah, distance on the left.
And distance over here,
100.
which we know is 100, sorry. So obviously t is going to be 1 hour. So with that in force, everybody got that? So then we'll look back at our problem where we say we have this vehicle and it's still traveling at this direction at 1 meter per second. We have the wave traveling back this way at 330 meters per second. So the setup for our problem is going to be such that in the distance that it's traveling, in that time, 29.9090909, I believe that's correct, right?
Is it one?
Pardon me?
Oh, I'm confused. Never mind.
That's right.
Well, that's because this is just 30 minus 0.09090909. So our problem turns out to be 29.909090991 is equal to t plus 330 t which is equal to 331 t, which is equal to t is equal to 0.0903598 seconds. And that's how much time it takes to go back. This is the returned time. So obviously the total time is equal to the first transmit plus the return, which is equal to 0.09090909 seconds plus 0.0903598 seconds, which is 0.181269 seconds. Would be nice if I actually set this up in a fairly decent way so I didn't have so many decimals for the demonstration, but I neglected to do that, sorry. So just to solidify this, to make sure that everybody can follow, I'm going to do the following example as well. And ask you to solve this. So the example. An automobile travels at 100 kilometers per hour. Pardon me? What is 100 kilometers per hour?
60 miles an hour.
About 62 miles an hour, right? I drive 62 all the time on interstate highways. So, assume an ultrasound system for the vehicle can identify a deer in the road at 500 meters.
How fast can the car be going before it hits the deer? With an acceleration of...
What's the brand of the car?
At what speed will you hit the deer now? How much time does this give? I don't even say how much time. How much distance? That's even easier. Does this give the driver to avoid the deer?
To avoid the deer.
How much distance does that give the driver to avoid the deer? Driver or automated system?
How much distance?
Yes.
500 meters.
Pardon me?
It's not that fast.
No,
500 meters.
go up the mountain.
By the time the signal comes back and identifies.
It's a little bit.
All right? So, in pairs, this is very similar to a problem I might give you on a test. So, spend a couple of minutes with somebody sitting next to you, and let's take a look at the solution. You never know, this might even show up on a quiz. All right, so we will do the quick solution for this. One thing, first off, is the speed of 100 kilometers per hour
That's a big decimal. That's a lot of gas.
is 100,000 meters per hour. And don't forget There are, in 1 hour,
Conversion.
3,600, oops, yeah, that's right, seconds. So the answer to this is 27.7, I think you said,
Yeah. What we got?
meters per second.
Dude, how you say 419? Don't copy this.
And this is the car velocity. So again, with the vehicle, that's my sports car.
That thing looks fast.
It's booking.
Not drawn to scale.
Not drawn. No, this is, well, I guess it's closer to a deer or a moose.
That might be like a.
It looks like a small sports car though.
So,
12.
it's yeah, that's my Miata, all right?
I didn't care
That
that.
gear is like a third the size of that car.
I just did like a couple.
Okay, so
Yeah,
it's a
it's
moose.
a 12 point.
Well, like
Or an elk.
It's driving Montana.
Yeah, you need way more.
It's a spike.
So again, we have 500 meters here, and the speed that we're running is, or the speed of sound, in this direction is going to be 330 meters per second.
What you gotta do is the time there, the time there, 14 meters there.
And so how long does it take to get there?
1.5.
1.5,
1.5, good enough, seconds. By the way, in that time, 1.515 seconds, the car moves 27.7 meters per second. And it's multiplied by 1.515 seconds. So the car moves
42.0875 meters.
40 or 42?
42.0875.
0.75
0875.
meters. So now we have to worry about the reflection. And again, it's the same problem as we've seen before. 27.7 meters per second. Something is coming at it at 330 meters per second. Our distance is going to be equal to, well, our distance was, what is this, 457 point, oh, I don't want to go.
9125.
91 meters is going to be equal to 27.7 meters per second plus 330 meters per second. By the way, that's also multiplied by some t seconds. So in the end, doing all the work, t is equal to,
You don't need T. You need distance, right?
When you first calculate the time, and then you
we got to calculate the time first. What is t?
1.387.
1.38?
I got
For the second
1.37.
part.
For the second part, yeah.
Yeah, 1.387.
Yeah, but I was 7.9, so I rounded it.
1.28.
I got 1.28.
28 or 38?
2.8. I have 3.8, but whatever.
You guys are all over.
Listen to me.
1.2799.
And so the distance the car travels
Can't see.
Plus 1.151.
Squiggle, squiggle,
2.7949.
during the 1.28 seconds times 27.7 meters per second is equal to
38.5.
35.46. So our distance away now, 500 minus,
Your number will lock, sorry, I don't be close enough.
say it again?
Wouldn't it just be 457.91 minus 35?
Yeah.
I'm doing the total distance.
Okay.
42.0875 minus 35.46 is equal to 419, you said?
Well, it's supposed to be, but.
I got two numbers that you for the.
1 to 22.
Say that again, 422?
Yeah, it's supposed to be 419.
I got 419.
I got 422. No, you gotta add up. Total distance, the whole distance, 22.07 meters there, 38.55 back.
All right, here's a question.
Would
Would this be like at night? Because wouldn't you see the deer otherwise? And the answer is yes. What's the whole reason for this? This is an automatic avoidance system where a person is not actually driving the car.
That's why I said 500 meters.
That's right, 500 meters.
For the car to be able to recognize that there is a
But you said
deer.
driver. See?
All right. The automated driver of the system
Now
who
you
uses
know.
sound instead of lights to
Good job.
detect an object in the way. So of course, if we're worrying about, if we're doing this with LiDAR or some sort of light-based mechanism, it's going to be a lot faster, right?
Yep.
So what does this tell you about ultrasound?
It's low.
It's relatively slow,
Oh, depends on what.
and in fact, one of the other problems with this is that ultrasound doesn't work all that well at great distances. Because it's a sound wave and it dissipates a lot faster than light. So perhaps to be able to avoid obstacles, you'll want to concentrate on something that is light-based. All right, so let's take a look at some other details associated with ultrasound. There are two ways that you can communicate with ultrasound. Or that I should say that you can control with ultrasound.
What type of technology do police officers use in their radar guns?
Radar?
Like, do they not use LiDAR?
They use,
They've got laser guns.
they have laser now. So it's a very similar concept with that. One thing, the question was, what do police use for speed detection? One is radar, which is very similar to ultrasound, right? But another mechanism that they use is a LiDAR-based or a laser-based mechanism. And the nice thing about, or at least with their tool, is that their beam is extremely narrow, as opposed to your typical LiDAR where you're at 60 degrees. This is bizarre. Stop. Here we go. As opposed to your typical LiDAR, which is 60 degrees or 120 degrees or maybe even a little bit wider, where you're making a big sweep. And in the LiDAR, when you're making that big sweep, you're actually limited by the speed of the mechanism that points the laser. Unless you have one of the technologies where you're shooting out more than one beam of light. Some of the more industrial types of LiDARs, like the SICK LiDAR. SICK is a S-I-C-K is a German company. They have lots of implemented devices out in the workplace, specifically in manufacturing floors for obstacle avoidance. You could run a forklift into these things and they won't break because they're solid steel, and the plastic lens is bulletproof almost. But if you start getting into the technologies that will be inexpensive for us, Hey, that might be a nice topic that somebody wants to look at for for homework assignment number 4. Then you'll have something that may have multiple pixels being sent out and recorded at the same time. And that's where you get your speed on that. But for police, they're probably just doing a couple of points and being able to do the triangulation on that.
My second question is there any way of like effectively changing what they get back?
Yeah,
Yeah,
Jammer.
there is.
it's
There
a
is
jammer,
ways.
and it's actually cheaper than than radar detectors because they're 100% illegal. But they go under your hood, and they have 4 points on it. So like there's a K60, which is like the best one, and there's 4 points on that. And it's just the front and the sides and then back. And so no matter what they shoot, you can program what they get back. So like you're going like 200 miles an hour, like just getting it, and they shoot it, and no matter what, it'll say 35 back.
But you know what?
You would make it that way.
I'll edit that out of the video. Okay, going on. Feel free to.
I forgot.
You talk to him during break. How about that? Right? Oh, I don't know where to go now with this. Oh, I know where I was going to say. To control ultrasound. There are 2 ways to do this. One is to give it a pulse. And at the pulse, there is the mechanism in the ultrasound device. By the way, typically one is a transmitter and one is a receiver. This is from the front. From the side, they look like small aluminum cans. When the rising edge of the pulse is sent, some simple circuitry here will actually send out the single chirp. Then, after a certain amount of time, this other part of the can will actually detect a certain amount of energy, a large amount of energy. And when it detects that, it will put a edge out there, which means that you have the following circuitry. You have some sort of CPU which is going to be connected to your ultrasound. And both of these are going to send pulses. So that means that the voltage on those need to be tied down. So you need to have some sort of pull-down resistor on that connection. And the software has to be available in here to either poll or work with an interrupt to be able to detect this pulse that comes back. So as you can imagine, how are you going to determine how far away something is? All right, the difference, size or magnitude? Oh, I should say that these are the same size.
Okay.
Same voltage. This is going to be 0 volts. This is going to be, let's say, 5 volts. It's going to be, there's going to be a certain amount of time, delta t, that is going to be represented by when the CPU puts the pulse out there and when the device returns and says, I heard something. Now what you have to keep in mind is that with a typical ultrasound device, if you're sending a pulse in, I'll even make this simple. If we're sending a pulse towards this flat screen, you're going to get a nice reflection back of just the screen. There will be some other noise or some other sound that might come back from this bucket. A mic that's empty bucket, all right? I might get a sound reflection back from this chair as well. But the most energy is going to be reflected back from the screen. The same will be true with identifying a deer. There will be a lot of noise out there from the road, but again, some of the reflection is such that if I were to send out a signal from here that way, it's going to reflect off the tabletop and go where? Back towards you? Hardly anything towards you. Most of it is just going to bounce off the surface. And what happens if something reflects off a surface? Kind of changes phase too, doesn't it? But in any case, when it reflects back off that wall, which is probably the biggest amount of energy that will be reflected back, that will be my pulse. The important aspect to think about this is when you're making when you're sending out a signal, or sending out noise, it actually has what's the best way to put it, a nice sweet spot, or what we call a beam pattern. So let's take an example. This is from the SRF 10, and this is a pretty readily available device. And so what it is saying is that if this is the center of your transmission, and you're sending it out, it does a good job of detecting devices or other things in its way between these angles here, which look to be about a nice 120-degree field of vision, and then its distance, it looks to be about 30, and I think this is 30 centimeters. This is meters. Let me look.
Minimum range 3 centimeters.
It's probably meters, yeah. So this is 30 meters away.
It says max range over there is 6 meters.
Exactly.
Okay. Then 6 meters. Let's see. So this, I guess these just mean energy. So this will be 6 meters is your maximum range. And what does that also tell you with respect to, is another aspect of this. What happens if I have an obstacle here in my beam and an obstacle up here? What will it give you data back on? The closest one. Because it's the first one it will encounter and send it back. So that's one disadvantage of an ultrasonic sensor, is that it will only give you one value. Infrared will do the same thing. So how do you think you would use that to your advantage, or now that you have that disadvantage, that you have this big wide range, how can you design your robotic system to get a better idea of all the obstacles that are out there?
Move the sensor.
Say that again?
Move the sensor.
All right, move a sensor. How do you move a sensor?
Move.
All right, what have you seen on the what do you call that?
A servo motor.
The servo motor on the Danny?
Definitely don't do it like that.
Got the cue card cycle. Switch.
And what else could you do if you weren't constrained by this
Map
sensor?
it, have it sit, scan 360, and then map.
Ooh. Do some mapping. All right? Or instead of having a beam that's 120 degrees, get something that's a lot narrower. And they have other devices. If we were to look up the SRF10 beam pattern versus some other ones, always in Google. Oh, look at that. I hit my nice little thing here. Let's look at an SRF 06. Images. I'm sure we can find And you probably have seen this before, right? In fact, this is, I believe, what it is that we're using. So in this case, maybe this is a nicer one to use because, wow, that's like 15 degrees. And which I'm going to see which one that is coming up. So this is the beam pattern for the SRF 4 and 5, as opposed to this one, which is the SRF 235. So the advantage of that is you've got a lot better range. Now notice here, communications. What is that? Digital, serial, I squared C. Well, one thing I want to point out is that here I showed one example of how you can do communication. Another one is literally to do serial.
Like DB9 and stuff like that.
And in particular, you have different types of protocol that are available. One in particular is called I squared C, in which you have 3 wires, and this is your CPU and this is your sensor. And between the two, you don't just do one of these signals, you actually send bytes. And in this case, the sensor is actually intelligent. It has its own CPU as well. So it does the same concept. It sends a signal out when you tell it to. You send it a byte to say, go sense. It'll then send a signal out. It'll receive the signal back, and then it'll return to you the actual value of centimeters that it measured. Actually, I think some of these might send back millimeters. I'll have to look at that. But instead of you having to do the calculation for time, it does the calculation for you.
We don't need the pulse one anymore.
Say that again?
We don't need the pulse one anymore.
And you don't need the pulse one anymore. But that means that you need a microprocessor or a microcontroller that actually will be able to do I squared C communications. So that is it for my for some initial discussion on this. Let's take a quick break because I see some people napping, and we'll come back in about 10 minutes. All right. So there is another concept associated with ultrasound where when you have, this is going to be one big long class, you know that? Where when you have a pulse sent by the CPU and the maximum distance would have been a pulse here, but it didn't come because there was nothing in the way. So you have your vehicle. We're looking down at our vehicle, and here's the sensor, and its range says, yeah, I can see out here, and there's absolutely nothing in there. So you expect at the max range that you will get some sort of signal back because it would have detected something in there. So what these devices will do is they have a little bit of smarts in them too. After something that's quite a bit of time, they'll actually will respond with a pulse. And what that's telling you is that, yes, I'm still alive, In other words, sometimes you don't know if the sensor went offline, if you're not getting a response back from it at all. So it responds back to you and says, yes, I received your pulse, I sent the ultrasonic sound, I heard nothing back. And that will be an acknowledgement pulse that should be way beyond what the maximum range of that rated sensor is. So in this case, if you said the sensor would come back in a signal and this would recognize 6 meters, maybe this is the time that would be equivalent to 12 meters, and your software has to be smart enough to know not to accept that as a distance, because it goes way beyond what the range is of that ultrasonic device. In other words, you have to write smart code. Shouldn't be that hard.
Sure.
But you'll never know when you have a need for, on your sensor device, or I should say in your robot, something that has a range like this, and something that would have a range like this. And you can orient them such that you can see things. That if there were an object here, it would only be seen in one of the beams. If something was here, it would be seen in both. If something were here, it would only be seen in this one. And this will, this configuration, to at least identify a rough location. So if your objective was to create one of these little vehicles that would follow someone, have we done that in this class?
Somebody did it with Lego, didn't it?
You did it with Lego, right?
Yeah.
And how did you do it? Did it move around?
Yeah, what it did was it sends. If there's nothing, then it turns 90 degrees and
Okay.
sends in that.
There you go. So what you did is very similar to this with one sensor. If you had two, you could have fired one and fired another. And actually, instead of pointing them both forward, you just point them off a little to the side, and some of the beam will overlap. Again, this is sound, so what happens if you do both at the exact same time? Right? You might have too much noise out there that one transmitter here will actually be picked up by this transmitter receiver over here. So you have to make sure that you are only doing one ultrasound at a time. And I think I mentioned this, the way to fix that would be maybe having two different ultrasounds with two different frequencies.
Yeah, to sample twice the maximum frequency.
Right. And I believe this is everything I wanted to talk about with respect. Well, no, I will do one more thing. And that is, in this situation, if we set our exceeded range signal was received after 75 milliseconds, what is the max frequency of a ultrasound system, sensor system, that sees nothing? So how often is that ultrasound system sending? Once every 75 milliseconds, correct? So the frequency is?
1 over 75.
Frequency is equal to 1 over 0.075 seconds, 13.3 seconds. Or 13.3 hertz would be the frequency. All right. That is it for infrared and ultrasound. Thank you very much.
Cheers.